Welcome to my Physics 1 Lab 1 report over constant velocity. My name is Christina Nielsen. Today in this presentation, we will go through an introduction about this lab, the purpose, and what we got from it, the experiment itself, an observe versus computational graph, and wrap up with some questions. Introduction. The purpose of this lab was to understand constant velocity as an object as it rolls on a surface, understand the forces acting on an object in terms of net force, and to compare constant velocity with observed velocity in the computational model of the velocity. Some assumptions that we took into account as we did this experiment were that the object is not accelerating, so the net force is 0, and that air resistance and friction are not acting on the marker in this lab. The only forces applicable here are the normal force and gravity. Some physical principles and models used. First, constant velocity. Because we are saying that the marker should roll with a constant velocity due to Newton's first law, we can assume that the net force here is 0, making the final velocity and the initial velocity equal, which is what we should see in the video. Newton's first law, and then average velocity. The average velocity should be constant throughout the video and is calculated using the average velocity formula seen here. Next, free body diagram. The marker is our system and the table is our surrounding. The free body diagram shows the two forces acting on the system, gravity and the normal force. In this example, these forces should cancel out to make a net force of 0. The experiment. Here's our video.
Here's the big issue.
We used an expo marker and a ruler as our calibration stick. Here we used the application tracker to create a computational model of the marker's velocity in graph form. We manually selected the position of the marker at each time step. We designated the right direction to be the positive x direction in order to get a graph with a positive slope. And we plotted each observed position at each time step, which then produced the graph you see to the right and the data set you see to the right of the graph. For our computational model, we set our marker to start at the origin, making the initial position the 0 vector. We then found the initial velocity and the mass from the data that tracker provided. We found the average velocity by adding the initial and final x positions from our data set, then dividing that number by the change in time from the tracker data. And we use this vector as the initial velocity because they should theoretically be the same for a constant velocity. The mass was standardized at 1 kilogram. Our time starts at 0, and we designated our delta t to be 0.017, which was the time steps used by the tracker due to the length of the video and the amount of position data points. We inputted the computational versions of the velocity and position update formulas that we got from the helpful coding tips in Canvas into our computational model in Python form, as you see closer to the bottom. If our marker should theoretically move with a constant velocity, our computational model data and observed data should match up in a straight line with a constant slope, right? Wrong. Observe versus computational graph. This is our graph. Although the lines are pretty similar, the observed data, which is the blue line, diverges from the constant velocity of the computational data, the orange line, before evening out eventually closer to the end. The observed line, or blue line, reaches a farther or greater x value quicker than the computational data does due to friction force and the initial push. Some possible error. It could be our video was not cropped to the right length after the initial push, or it was cropped before the initial push. The video was not long enough to fully see the effect of the outside forces on the marker, or the shape of the marker could have been an unaccounted for force factor for the marker's movement. Some questions. What if the positive x and negative x axes were interchanged. The signs of the position and velocity would change, producing the opposite slope graph. However, all magnitudes would stay the same, producing the same result, just a different graph and different signs. Is it possible to determine the number of pushes and pulls in a net force of 0 in this lab? No, it is not possible to understand the number of pushes and pulls that add up to a net force of 0 because all we know is that the n number of forces cancel each other out.